Hey kids, so today you might have already watched some of the other magnetic lessons on magnetizing and then on temporary versus permanent magnets. I want to talk briefly about poles with you today. We've studied poles, magnetic poles, north and south poles. We've studied those in class during our magnetizing lesson, and as you've learned, to magnetize means to become or to make a magnet. Well, there's a lot of relevance with poles in that. Take a look at the poles in these temporary magnets. Um, this could represent a paperclip, and we could use tweezers to represent the poles you see below here. So take a look at the inside of a paperclip, and you can see that the north poles are all facing different directions, and then the south poles in green are all facing different directions. You'll notice that none of the north poles really truly face north inside the paperclip, and inside the paperclip none of the south poles truly face south. Same thing with the tweezers. If you look within the tweezers, inside the tweezers, the north poles inside of it don't really truly face north. Okay, and that's shown with the red squares, and the green squares would represent the south poles. They don't truly face south. And a couple things you have to realize. First of all, is that the paperclip, the tweezers, they're all made out of iron, so they're ferrous objects. But the thing is that they're not magnetized. All ferrous objects have poles in them. They have north poles and south poles. Anything that has iron in it has north and south poles in it. So whether it's the nail, the paperclip, the tweezers, anything that has iron is considered ferrous, and anything that's ferrous has north and south poles inside of it. Now, these poles have not been magnetized. These poles have not been aligned. If I were to magnetize the paperclip or the tweezers, in other words, if I were to make the paperclip or the tweezers into a magnet, a temporary magnet, the poles would then align. And you've seen this in the other videos, and I'll demonstrate it again. But when you magnetize a ferrous object, what you're doing is you're first realizing that the ferrous object does have north and south poles. But because it's not yet a magnet, those north and south poles, they look jumbled up. So they look like in a paperclip or tweezers, they look like this. None of the poles are aligned. The north poles face all different directions. The south poles, they don't face south, they face different directions. But I'm going to magnetize the paperclip, for example, by aligning these poles, making them straight. And I'm just pushing all the north one way, and then the south, because it's north and south, they attract. You're going to have your south facing one way, your north facing another way. And what I'm doing is I am aligning these poles so that they face in the direction they're supposed to. I'm magnetizing this paperclip like this, and same thing would be done with the tweezers in a straight motion, so that you are not mixing the poles like this. You would not want to align poles like this. You couldn't align poles like this, because then you'd be jumbling them up. What you want to do is you want to push north in one direction, and then south will go in the opposite direction. Okay? And so what happens is, being a ferrous object, it has the poles, and when it's magnetized, what I just did was, the poles inside these objects, they align. And you can see the alignment here now, as you've seen in the previous videos. North face one way, and they all face north actually, and then south face one way, and they all face south. So this is an example of, you could call this a ferrous object that has not been magnetized, and this you could call a ferrous object that has been magnetized and that now is a temporary magnet. This paperclip, the tweezers, the nail, they are magnetized. Once I magnetize them, and their poles, north and south, face the appropriate direction, and they're aligned. But after a few moments, the poles of the paperclip, tweezers, and nail, they're just going to go back to being like this. So this is a magnetized ferrous object, not magnetized ferrous object. You can do an experiment in class with this. Here's a here's a question that I created, and you can create your own questions, but this question has to do with temporary and permanent magnets. It has to do with magnetizing, and has to do with ferrous objects. And my question that I could try to find the answer to is, which ferrous object becomes the strongest temporary magnet? So if I were to look, for example, at the paperclip, the tweezers, or the nail, they're all ferrous objects. Which one of these would become the strongest temporary magnet? So you know they're all temporary. Which of these would become the strongest? And you can do a test to see which ferrous object becomes the strongest magnet. And then when you look at temporary magnets, you have to ask yourself, which temporary magnet has the strongest magnetic field, and can you actually see the magnetic field on a temporary magnet or a permanent magnet for that matter? Thanks.